Okay. Yeah. Hello everyone. So let's get started. The title of this talk is Curse of Depth in Large Language Models, and the outline is basically three part. I will briefly introduce the background of efficient LM. Then I will tell something. There is some ineffective layers in LMs, and how can we leverage it for efficient LMs? And then is the main topic, which I'm currently working on, is curse of depth in large language models. So first, I believe I don't have to convince everyone. Like AI model is so powerful, but very expensive. We want to make it efficient. It's expensive at both training and inference. We want to make it as efficient as possible. And there's many bottlenecks for efficiency. This talk I will mainly talk about not only about inference but also training. So for inference, there are basically three bottlenecks, which is the massive size of the model, and it requires so many blah blah GPUs and basically 5 more A100 to only load the GPT 175 billion model, which is already outdated model. And also there's a KV cache problem. If you want to do long context reasoning, your KV cache will also consume a large amount of memory. And also there's a quadratic cost of your self-attention located in transformer, which also quite expensive. And there's people you can just reuse the techniques pre-LMs to make LMs more efficient. Like you can do sparsification, you can decide which neurons, which weights, or even layers are not that important. You can just sparsify your model to make your model smaller. And also you can use quantization techniques to mapping the high precedence members to low precedence members. This is quantization. And also you can do low rank approximation, like you can use SVD or PCA technique to project your big metric into subspace, make it more efficient to load and to fine tuning. And so the and I have done the research in this field for a couple of years, and there's I have my own one-trick pony in how can we make LMs more efficient. That is, you can always compress the layer that are less effective more. I mean, some layers are not as important as other layers, so you can prune them or you can quantize them stronger, harder, and you can make just to increase your compression rate. And the question here is, where are these effective layers in LMs, and how can we measure the effectiveness of layers in LMs? So the first part is about this topic, and we have a solution which we called outlier weight layer-wise sparsity. So essentially it studies how can we measure the layer-wise importance when we do pruning. But the technique here can also be leveraged to other compression techniques like quantization, parameter efficient fine-tuning, etc. And let's dive into it. So the notation of this talk is like this. The x, we assume we have a input x, and the weights w with the wij means connects the j's input to i's output. And the sparsity is some common metric used to measure how many the ratio of zero weights in your model. And there's a performance metric called the perplexity, which is widely used to measure the capacity of your model. And the architecture I will mainly focus on decoder transformer. And what is pruning? Pruning is a long-standing techniques in LMs in deep learning. Like you need to figure out, you need to remove some unimportant components. They're either unstructured way, like irregular pattern of your weight metric, or you can do structure pruning. You can remove this neural, this two neurons, or even you can remove the entire layer, which are more hardware friendly. That's called structure pruning. And based on some metric, like for example, weight magnitude, or the the performance, the output difference when you remove the one component. So that can also be a pruning criteria. And the goal for pruning is you just remove the unimportant components that you think related to the task, then make your model more efficient, or make a sparse model. And before LLMs, there's one most successful and robust pruning metric is magnitude pruning. As we can see on left side, we have convex. We perform magnitude pruning on convex on ImageNet. We can see this is a one-shot pruning. We can easily remove 60% of weights without significantly drop performance. You can still have roughly 80% accuracy. However, if you do it on LLMs, there's an OPT 170B model, you can, with the magnitude pruning, you can only drop or prune 10% of weights out of your model. And then your model starts to lose performance significantly. The reason behind behind this scenario is people generally believe outliers is something very important in LLMs, which means there are some channels of your output whose magnitude is significantly larger than the rest of channels. They call it activation outliers. And if you only consider pruning with weight magnitude, for example, W here is weight metric, and X is input or the output. If you only consider, let's say, weight magnitude, you will likely remove or disconnect your connection to the outlier input or outlier output. So this is why there's a paper called Wanda. They propose a new pruning metric, by claiming they consider outliers of your model. So given the fact that outliers are important, and our paper trying to prune based on the outlier of your model, but also consider layer-wise sparsity. So the rationale here is we still want to prune the layers prune more the layers that are less important. But how can we measure these outliers? The importance we will try to consider the outlier ratio. So here, before we pruning, we first calculate layer-wise outlier distribution, which is designed as follows. So first, step one, we first assign an outlier score for each weight. This basically is the pruning metric of Wanda. So basically, we assign each weight with metrics used to measure the outlier score. And then we calculate the ratio of the outlier weights in each layer, like to measure. So there's a typo, like here it is not it should be on this L means the which layer. And after we first calculate the mean value of outlier score in each layer. Then we calculate the outlier ratio as DL, which essentially measures how many weights whose outlier score is tau times larger than the average score in each layer. And essentially we means if the layer has more weights who has very larger outlier scores, we will treat it as outlier weights. And after calculates DL, we will have a layer-wise DL, which essentially is a distribution of a layer-wise outlier distribution. And we can say the very interesting pattern is y-axis is the layer index. You can see the earlier layers always has larger outlier ratios than later layers. This is a llama model. And this is something we want to measure. Let's indicate how important a layer is. Basically, we say the higher outlier ratio means this layer is more important because probably we believe the more important layers will receive larger gradients, so they tend to have larger weights or larger activations. And after we get this outlier ratio, layer-wise outlier distribution, we uh, we calculate or we recalculate the layer-wise sparsity by reversely to this ratio, which means if the outlier ratio is bigger, then we assign a lower sparsity, a lower pruning ratio to the layer. So but in the end, we will have something like this kind of layer-wise sparsity ratio. And then we can assign we can perform pruning based on different pruning metric and based on this outlier ratio. So as I said, this is basically a layer-wise sparsity ratio, and you can combine this out ratio with different pruning metric, or like one dot or sparse GPT, or even magnitude. So by combining this layer-wise ratio, you can consistently observe performance improvement, especially at a very high sparsity, like here is 70% sparsity. You can reduce the perplexity significantly. And uh, and another benefits of for sparsity pruning is can bring you real time speed up. Even it's not that friendly on GPU, but on CPU level, you can achieve a significantly speed up. So we use the deep sparse inference engine, and we measure the throughput and speed up of different sparsity. Now you can see at 70% sparsity, it gives us 2.6 times speed up. And what is more interesting, if you manage to sparsify your model at 90% sparsity, it gives you a very promising speed up, like 4 times speed up, which is quite significant. But the problems, can we compress our model by 90% without performance drop? Maybe we can. I mean, after doing pruning for so many years, I think what is more important is like if you can perform sufficient training or fine tuning of your prune model. If you have computation to do long time fine tuning, you can basically prune your model to a high sparsity level. Okay, so we have done the first part. Like we know there are some layers that are not very effective than other layers. It is on one side, it gives you indicator like how can you make your model more efficient. On the other side, what I believe is that means some of your model are not that well trained. Given the massive or so expensive the training, how expensive the training it is. If we can manage to make every layer equally contribute or well trained, probably we will be more closer to AGI. So this is my belief, and if you measure the layer-wise outlier distribution of different llama model, so these are different size, you can see there's this very a consistent pattern of the outlier of the layer-wise importance. All these models, their deeper layers are not very useful. You can just remove them. I mean, not totally remove that. I mean, you can remove them. They don't hurt performance too much. So the curse try. I first personally I identify as a pitfall of training, and I want to address this training problem. So we propose curse of depth in LLMs, which is defined as the deeper layers in LLMs contribute significantly less than to learning and presentation compared to layers. I'm not saying that it's contribute nothing. I mean, it contributes significantly less than other layers. And my thought, as I said, ideally, we want all layers to be well trained with a sufficient diversity in feature from layers to maximize the utility of network parameters or our training resources. And to solve this problem, we first need to understand what is the root cause of ineffectiveness of deeper layers. Why the deeper layers obviously deeper layers doesn't contribute too much. And my answer here, you will have your own answer. So my answer here is because the widespread usage of pre-normalization. So there are basically two main normalization. There are many more, like sandwich layer norm, different layer norm. So two layer norms are most widely used. Well, first is post layer norm, which means we do layer norm post the addition of your attention layer or sub layer with your residual connection. And what is more common recently for this model LLMs is pre-layer norm, which means you normalize your input before your sublayer. It's either attention layer or FFN layer. So you don't really constrain, you don't really care this residual connection. This is a widely used pre-layer norm, which is used in Llama or Mistral or DeepSeek. They both use this pre-layer norm. And this is the answer of ChatGPT when I ask what is a layer norm, how it works. It mentioned layer norm is a key component in transformer used to stabilize and accelerate training by normalized input to each layer of the network. And my hypothesis is the inefficiency of deeper layers primarily stems from choice of layer normalization. Specifically, pre-layer norm tends to produce smaller gradients in deeper layers, thereby has more effective shallow layers. So their deeper layers are less effective, shallow layers are more effective. Post-LN basically have the opposite trend. So it results larger gradients in deeper layers and small gradients in early layers. So opposed element has a different trend of layer importance. I will demonstrate it in the follow evaluation. So we first evaluate this hypothesis empirically. The methodology here is how about we directly measure the layer-wise importance of models who is pre-layer norm, and another one is post-layer norm. So we have two categories. One is open weight large LMs. We choose Llama 2 as pre-layer norm, BERT large as a post-layer norm. And also, because the only difference between Llama and BERT is not only, there's many difference between these two models, not only layer norm. We also train our own LMs. Basically, we train Llama 130 million. With the only difference is one is trained with the pre-layer norm, one is trained with the post-layer norm. And layer-wise effective metrics, we choose three metrics. One is angular distance between layers. So we believe if the layer has smaller distance than its adjacent layers, that means its row can be replaced by other layers. So it's not that important. And also another metric is performance drop of layer pruning. So if after removing this layer, the performance drop is marginal, which means it doesn't contribute too much to the task. And we also draw the gradient norm of each layer to demonstrate how the gradient dynamics change across layers. So here is our open weight large scale LMs. And you can see we put BERT model on the left hand side, Llama model on right hand side. We can see the top figures are angular distance. So yellow color means the layer is more similar or has smaller distance to its adjacent layers. And the performance drop is here. This is the performance or accuracy changes after you remove each layer. So bigger values means the larger performance drop after we remove certain layer. And we can say for BERT model, which use post-LN, the early layers are more similar to their adjacent layers or next several layers. You can see the most yellow part are located in the early layers. And if we remove certain layer of early layers, their performance, this is performance of a squad, performance drop of squad. You can see if we remove some early layers, the performance doesn't change too much. And however, if we remove some later layers, the performance drop of BERT large will significantly. But things are very opposite for llama model. So we also drop the layer-wise similarity. As we can see, the most similar layers are located in the deeper layers of llama, which is pre-layer norm. And if we remove these deeper layers, its performance on MMLU doesn't change too much, which means these deeper layers you don't contribute too much to the MMU datasets. And there are more models, and we also evaluate different kind of models. So except for BERT, we also try Mistral, Craven, DeepSeek, Llama 2, 7B to 13B. So only exception is BERT large, which use post-layer norm. The rest model use pre-layer norm, and all of them, the deeper layers doesn't contribute too much. And this is quite consistent. And our in-house small-scale LLMs also have the similar trend. So if you this is a post LN again, their early layers are less effective. They're more similar to their adjacent layers, and removing these early layers doesn't hurt performance too much. And pre-layer norm, they have again similar trend. Their deeper layers are more similar and has less effect on performance if we remove this layer. And this is a gradient norm. You can see post-LN tend to have larger gradient norm on deeper layers. Pre-LN tends to have small gradients on deeper layers. So I hope this empirical study has proved my hypothesis. Like this is the choice of layer norm actually has an effect on your layer-wise importance. And we also, beside this empirical evaluation, we also have some theory intuitions here, which actually is asked by reviewers, not myself, but it is a good to have some theoretical insights. So let's see. This is a formulation of post-layer norm. So you apply a layer norm after your addition of your input or residual block with your sublayer. And pre-layer norm, you put layer norm only on before the sublayer. You don't actually constrain the residual connection. And if you calculate the derivative of post-LN and pre-LN, you will have this. And something very interesting is both equation, they have this part, which means is essentially the Jacobi metric of your layer norm to the input of your layer norm. So they essentially the same part. And both of them has this part. If we have this assumption, like if your input follows a normal distribution with a mean of 0, and the sigma x is a variance of your input x, this Jacobi metric of your layer norm can approximate to this value, which means is opposite to the sigma x, or the variance of your layer norm input. Which means if your variance, like here, if the if the variance of your input to your layer norm is too big, this part will approximately equals to 0 if your variance is too big. And this actually is true as your model accumulated with many layers, because for pre-LN, like you don't actually constrain your residual connection. What you only normalize is this path. You don't constrain this path, which will cause your variance to become too big during training. We have some results to prove this, but the insight here, if your variance is too big, it will mix the Jacobi matrix of your layer norm to 0. If you look at here, if this is 0, which means the derivative of pre-layer norm will equals to an identity metric, which means the deeper layers will only perform as identity mapping. So they don't contribute to your gradients. They just propagate either forward propagate or back propagate the signal without adding any useful information. And post-LN, if this part is 0, or either this part is too big or too small, it will cause gradient vanishing or gradient explosion. So in summary, so the layer norm, the Jacobi matrix of layer norm just cause different behavior of post-LN and pre-LN. For post-LN, if this part, because they don't, this part is directly multiply this part. If something is off with this part, the post-LN will either suffer from gradient spike or gradient vanishing. The good thing of pre-LN is because we somehow isolate the gradient mapping out of this part. So if something is weird on this part, is either equals to 0, we still have identity mapping. It still can perform function properly. It just doesn't contribute too much. This is our theory understanding of this problem, and based on this our analysis, we first propose Mix-LN to solve this problem. So our insight is, okay, pre-LN tends to has very good pre-LN tends to have very good later layers. Post-LN tends to has pre-LN tends to have very good early layers. Post-LN tends to have very good later layers. How about we combine them together? We just make these middle layers more useful, and on the other side we can reduce the depth of each layer now. So we first our proposal is we first train we put post LN in first alpha times L layers. So alpha we usually choose a quarter of layers as post LN. Then the rest layer we choose as pre LN. And here is our angular distance visualization, and we can see our intuition is we want to make the middle layers more useful. So you can see the middle layers of Mix-LN indeed are more different. It has bigger distance than its adjacent layers compared to pre-LN. So pre-LN, the middle to deeper layers tends to be more similar, and post-LN also their early layers tends to be more similar. But our method, if you combine them together, you will have quite strong or different diverse middle layers. And if you remove the middle layers of a Mix-LN, you can see the performance drop is bigger than pre-LN. And this is a gradient norm. And the red color is Mix-LN. You can see the red, even though it still have this trend, the deeper layers tends to have smaller gradients because we reduce the number of layers of pre-layer norm, so the trend is can be mitigated. The performance is okay. Like if we combine them for different size, even for 1B, we manage to reduce the perplexity significantly, and the benefits can also be extended to supervised fine-tuning. However, okay, this is I have to admit that in order to achieve this performance, so we can see the Mix-LN actually performs quite well on small model size, like 130 million or 250 million. It's up from pre-layer norm. But once the model size goes up, like we can, or the training token becomes bigger, we actually observe very bad stability of Mix-LN because the use of a pre-layer norm, the use of post-layer norm. You can see if you use post-layer norm, once you start to train with a bigger model, your perplexity start not converge. So I think ideally we want to solve this problem without involving post-layer norm. So this post-layer norm, I haven't figured out why, but intuition here, the post-layer norm tends to, because post-layer norm doesn't isolate the identity mapping here. So once this part has some issue, your model will convert. You start to diverge. So the post-layer norm is just very difficult. We will suffer from training if you don't fine tune or don't give enough warm up time or you use too large learning rate. Suppose the layer norm is something I trying to avoid during training. So if if Mix-L is hard to scale up, how can we solve this problem? Maybe if we look back and here, we will have a different solution here. So the root cause here is if the sigma x or the input variance of your layer norm is too big, this part will become 0. So one solution here, we constrain it. We don't let it to become too big, because as I shows here, this is the average output variance of your model or pre-layer norm. You can see from color blue to red, the layer accumulated. So you can see as training, this is update step, as training goes on, you can see the variance of deeper layers start to grow exponentially than the early layers. So this actually verifies my theory that like the sigma x will becomes very big as training goes on. So how about we find a way to constrain the variance? So our fix is very simple. So we propose layer norm scaling. So after layer norm, we trying to scale down your output of a layer norm by reversely to the square root of your layer depth. So the L is not capital L, it's a small L, which means the current layer depth. And this works really well. And you can see here is the visualization of output variance. So this is layer norm, and there people trying to constrain the variance at the initialization, and this actually was used in GPT-2. At the initialization, they scale down your variance of your weight metric. This is called scaled initialization. Basically what they do is similar to our method, but they do it only at the initialization. But our method is we trying to scale down your output variance during retraining, because every time we will scale down, every training time step we will perform this scaling down. So our method is more like it can control the training dynamics. It performs as training goes on. So this figure, what I mean is, it's not enough if we only constrain, only we perform scaling down at initialization. You can see even probably it will constrain, it will works at the beginning, but as training goes on, the variance starts to become larger again. And you can see after you applying layer norm scaling, we can control the variance to below to 25 compared to without constraining 175 or compared to scaled initialization. And with these tricks, we can finally successfully constrain. We can scale. We can achieve quite consistent performance improvement on different model size. And this one benefit is like if you scale based on the square root of your depth, you don't need any hyperparameters. It just is your scaling factor will be your layer depth. This is another benefits. Okay, and I didn't put results here, so the results can also be extended to self fine-tuning or reinforcement learning alignment. Okay, and here are more evaluations. So before what we evaluated is only like here. The layer drop is something very simple task like MMLU without involving any thinking property. So we were asked by other people like how about we measure the layer-wise importance on some difficult task, something like math reasoning involving long thinking, long COT. And we measure the performance of Quaven 2.5 math with R1 training and without R1 training. We indeed observe an opposite trend. You can see very interesting. So this is a layer performance drop of a layer pruning. And you can see if we remove certain layer at early layer, the performance drop starts, it doesn't suffer from performance drop at all. And this is consistent with the R1 model and without R1 model. So we observe a very different trend, exactly opposite trend than previous model. What does this mean? Does it means it's the long, like deeper layers are more important for long thinking? And to answer this, we also measure the same task, the performance on same task performance on Llama model. And we can see again, this is aligned with our observation. For Llama model, Llama 3, 8B, either R1 or non-R1, we can again see this later layers doesn't contribute too much. So same task involving math reasoning. Exactly, this is a very different trend. Both Quaven, their early layers are not important. Sorry. Llama model, their deeper layers are very important, very unimportant. So I think even maybe the task difficulty will plays a role here. Like in general, we believe that the harder task, we will need more parameters to behave. Like people generally believe we need deeper model to perform reasoning, but this will only influence how the contribution, like it won't flip the contribution. What actually flips the contribution is architecture. So here we indeed observe the Quaven model after the first version of Quaven, they start to have a different model architecture. So the first version of Quaven is exactly same as Llama model. So after their V2 or V2.5, they start to have a different model. The model tends to be uh, fatter, but shorter. So it tends to, I don't know how they find this model performs so different. Their model is just shorter and fatter than Llama model. I think this is the root cause of why Quaven behave so different from Llama. And you can see the Quaven 2.5 and Quaven 2, they all has they're very let's say not useful early layers. Their early layers doesn't contribute too much. And we are still trying to understand what is root cause, because Quaven also use pre-layer norm. They use pre-layer norm, but their architecture is different from their previous one. And we trying to train a Quaven model from scratch. We do observe like their early layers are not important. So my conclusion here is the choice of layer norm is one factor that influences their layer-wise importance. And also you can also influence this by better design of your model. So maybe there existing a better depth width ratio that can help your model learn more effectively. So we are trying to study that question. Okay, I don't know how many times I have. Here is the conclusion of this talk. No, maybe this is a future work. The future question I'm very interested in. So why Quaven 2 is so different from Llama or its first version? And another question is how to further leverage curse of depth for LLM compression. So we have show pruning works, okay. They must also work for quantization, for KV cache compression. You just, how can we better leverage this for LLM compression? If you're more care about the utilization of your resource, maybe you can propose, like me, to propose some method to solve the curse of depth. Because what we do is only we need to train from scratch to fix this problem. But most model actually are already pre-trained with massive computing and data sets. How can we solve this curse of depth in post-training, not like training from scratch, which is not affordable to people like us? And also another interesting question, can we mitigate the curse of depth by optimizing with depth ratios, like what prevalent does? Okay, yeah, this is my talk, and feel free to ask any questions.